All right, let's get started. Good morning, everybody. It's really so nice to see all of you here, especially on Thursday morning at 8 a.m., knowing what all happened last night. So first, thanks so much for coming and wanting to be part of this session. We're going to have a lot of information. We're going to have a lot of learning and hopefully some fun as well. So before we get on with the session, so today's session is I like to call it Hangover Part 4. So a quick show of hands of how many guys here went out for the appreciation event last night and then gambling all night and then just turned up here directly. Well, I have some gift. I did have a nice little gift here for somebody who did that. Well, if someone did that, I'm sure they're most interested in this session, right? So, all right. So Hangover Part 4 is just going to begin. I also have another jab at this session because I think I'm also competing for one of the longest titles in any of the Cisco Live sessions. I'm sure a lot of you have noticed it. For those who really don't care for that, it's just a session on FEX or Nexus 2000. And we'll go pretty much in depth in a lot of areas, right? Architecture, design, and we'll look at a whole bunch of things. Before we proceed with the agenda and what we're going to do today, a small introduction about myself. My name is Pawan Kaushik, and I'm a TME, a technical marketing engineer with the Nexus business unit. So I deal primarily with all the Nexus 2000, 5000, 7000 range of switches, 6000 as well. And apart from that, I also specialize in certain technologies like ITD, the Intelligent Traffic Director, and a few other things. So I've been with Cisco for close to 8 years now, and I've had a wide area of expertise in troubleshooting in pretty much in the whole of switching. So I've worked with all Catalyst switches. I've worked with most of the Nexus product family. I've been troubleshooting networks for quite some time now, for about 6 years, and now I'm a TME with the data center group. So that's as much about myself, and let's get started. Quick show of hands of how many people here have never heard of a FEX before? Anyone who has no clue of what a FEX is? Okay. How many FEX gurus in the house are here with 2 pages full of questions all written down to pow, 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 fire at me?
I had it, but I forgot it in the room.
Oh, thank goodness. Okay, so, well, no problem. There's something in this for everybody. Okay, so what I like to do is to go through the session goals, right? So this is a product session, and we're going to focus in depth on the product. We're going to look at a lot of features and capabilities as well. We may not go in depth on each feature because 2 hours is a long time, but once we get started, you'll realize that it's just way too short to go in depth on any specific feature, right? So we will talk about what the Nexus 2000 is, what are the parents that support Nexus 2000. We will discuss all the architectures, design, and topologies that exist with Nexus 2000, how you can deploy Nexus 2000, what makes sense, what does not, what is supported, what is not, best practices, and a lot of these things, right? What we will not cover, however, is, we will touch upon topics like VPC, FCOE, FC, ACI, QoS, but troubleshooting also, but we will not go into depths because each of these are, an entire session in themselves, right? So I'm available after this session, and I'm happy to take questions as they come along, but I'm also available for any specific questions you have after the session, so feel free to reach out to me. Well, we are in the middle of a casino, so there has to be some house rules. So we have about 4 Nexus 2300 switches here in the room. So I've laid it out at different points on the tables here. So now or a little while after the session, maybe feel free to go and have a touch and feel of the box, look at what it really is, and then maybe that will help you also connect with what we look at just photographs here. Please do keep the session interactive. Do ask questions. But if there is something that's very detail-oriented, I'll probably keep that for offline, so we don't hog up a lot of time on specifics. Okay, with that, let's get started. So our agenda looks like this for today. we will first do an introduction. We'll do a context of what the Nexus 2000 is. Every now and then, we'll wake people up from their slumber. I've got some amazing gifts for you guys here. I've got coffee, aspirin, and all those things that you want right now. Well, who wants selfie sticks? Who wants, LED torches? Nothing like an aspirin in the morning, right? So I do have some genuine gifts, not aspirin, but I'll ask questions here and there just to keep it interactive, and let's see who gets them. We'll finally go into the Nexus 2000 itself in detail, but we'll also look at how they connect with the parents, what are the design features, architectures that you would want to do, and a few snippets, and as ACI and all of these are very popular now, a couple of snippets of how you may be able to configure effects with ACI, and things like that is something that we will focus on in this session. Okay? Fundamentally, let's get a few things straight. Even if you guys don't go out of the session with, even if you've forgotten most of what I said, this is one thing I just want you to take away from the session, right? What is FEX? So for those of you wondering what is a Nexus 2000 and what is FEX, they are the same thing. So the FEX is simply a cute little name for a fabric extender. So the idea of modular switches is something that most people are comfortable with. You've got one huge chassis that sits in one place. You can't really break a chassis and put parts of a chassis at different places. You have line cards and you put them into the modular chassis. And well, there you have your switch. Now, in certain architectures where you have a rack full of equipment, you've got thousands of servers, you may want to actually keep a different part of your aggregation at each row in the rack. So there comes a concept where you consider a virtual switch. Think of a couple of parent switches, like the ones you see in the topmost part here. Oops. So the topmost part here, you see a couple of switches like the 9000, Nexus 9000s, maybe the Nexus 5600s. But then think of all these smaller switches that really don't go into any chassis, but they connect logically to each of these parents. Now, while this diagram looks identical, they look like they're all in the same place, you can actually move them out to each row. So think of each FEX as an extended module of the line card. So the best way to define a FEX and to really understand what a FEX is the FEX is simply a remote line card, right? That makes sense. So it's just one switch that spans your entire rack, and you just have one line card of each switch on top of each rack. Well, that's as simple as it gets. So fundamentally, they're identical to having like an extra line card in the system and having that line card pushed out to serve each row in the rack. Now, in this example, I've actually showed you a couple of fixed parent switches. So the switches you see up there are not modular themselves, but the fact is that you can also use something like a Nexus 7000 here or a Nexus 9000. You can use that chassis and still also connect FEXs to it. So the parent does not have to be a fixed configuration switch. You could do this, and you could also have a bunch of FEXs hanging off of there. So that's all there is about FEX. So I think you guys are experts on what a FEX is right now. The whole concept of FEX brings a very interesting proposition to the table. Instead of having individual switches at each point, what you get is you get an extremely simplified top-of-the-rack solution. So for any of you there wondering what is top of a rack, it's the type of connectivity in which you have a huge number of ports required in each row on the rack. And as a result, one switch is not good enough for the entire row or the entire rack. So you need one switch on top of each rack. Now, imagine if you have about maybe 25 rows in your rack, and a reasonable estimate. You need 25 top-of-the-rack switches. The top-of-the-rack switches then connect to another aggregation box that's at the end of the row, and then that would in turn connect elsewhere. Now, imagine if you have 10 rows, 10 racks like that, you're talking about 250 top-of-the-rack switches, right? Have you considered the fact that you will actually have to manage 250 individual top-of-the-rack switches? That's not easy. That's not nice. So that's where FEX gives you the one biggest advantage. If you had to say one thing about what is great about a FEX, The simple fact that it's managed through one single entity, which is the parent switch. So even if you have 30 FEXs connected to a parent, they're all logged in through one box, which is the parent switch. You have a simplified management as well as troubleshooting, configuration, or verification. Everything is simplified because it's controlled through the parent. And also, as you can see here, we support it on all our Nexus major platforms. Now, a small word, since there are so many different switches and so many different FEX models, which model is exactly supported on which platform is something you have to refer to the matrix. But in general, FEXs are actually supported across all the platforms. Nexus 5K, Nexus 6K, 7K, and 9K. What I would ask you to do, and this holds true for the entire session because there are more switch models than we can count, and there's more FEX models than I can count in my hand. So there's going to be a huge matrix, and I can't go through each and every combination here talking to you guys in the room. So what applies here for the whole session is when I say that a feature is supported, it means that it's supported in at least a few combinations of FEX and parent. If you have a specific combination in mind, the data sheets, the compatibility guides, and the feature configuration guides would be the best point for you to verify your model of FEX and your model of parent switch to make sure that they are compatible. Now, lastly, how many people here understand what a unified port is? Well, that's a good number. So when you're talking about unified ports, FEX again offers one more great advantage that you can combine your storage and Ethernet networks into one single domain. And what the 5K, 6K actually has achieved through the UB ports on the parent itself, we now also support that on the FEX, individual FEX boxes. So more about that later. We'll take a deeper look on that. So I'm not going to discuss this slide in detail. I like to explain stuff more than just call out what's there. This is there for your reference, and these are all the benefits that you actually get from using a FEX. So obviously there's CapEx, OpEx savings because you're managing everything from a lower cost platform that integrates into one management parent switch. It's also agnostic to the underlying fabric architecture, meaning ACI is also supported. FEX is supported through ACI, FEX is supported through your traditional fabric architectures. And from a performance standpoint, even the FEXs have been moving ahead in terms of generation. And as the requirement for performance comes up, we have higher performance FEXs which are suited for certain workloads. So again, we'll talk about each of these in specific as we go forward, right? So how many of you here have never heard of ACI? Well, that's a relief because almost everything that goes on in Cisco Live is pretty much about ACI. We have a good small snippet where I show you how you can configure FEX through ACI. So ACI is something that's really the thing that's the next gen. It's a fundamental shift in how we're going to work on networks, and it's also useful to know that FEX Nexus 2000 is supported across ACI as well. Okay, so enough of context, enough of just beating around the bush. Let's get into the meat of the subject. Let's take a look at all the parent platforms. Most of you would know most of these already, but just for the sake of anyone who does not know a particular platform, we'll take a quick look at what the parent switches are and what are supported. The Nexus 2000 platform is supported on the Nexus 5K and 6K platforms. It's also supported on the Nexus 7000 and 7700. And also your Nexus 9000, which is basically your Nexus 9300 and the 9500. So there is complete interoperability between these platforms in general, and we will take a look at each of these platforms to understand what is available. So with the Nexus 5K or 6K platforms, the 5600 represents the latest generation of switches. A big reference here for you for what these platforms can do. And as you can see there is definite support for FEX on all these platforms. So you can use a Nexus 5600 and couple it with FEX to get the benefits of this architecture. The Nexus 7000 platform comprises of the Nexus 7000 and the Nexus 7700. Okay, I've got a selfie stick for somebody who can give me what's the most fundamental difference between a 7K and a 7700? Yes? Okay, that's correct in terms of the bandwidth that's supported. there's a selfie stick for you. But one of the places where the 7700 makes a big difference is the density of whatever ports you're talking about. So what a Nexus 7000 can support in one module, ideally that slot in the 7700 typically supports twice that much. So it's similar to a 7000 in basic architecture, but it's a high density platform. So we have a whole bunch of 7700 chassis, we have a whole bunch of 7000 chassis, and FEX is actually supported on all of these as well. A quick reminder of the evolution of the 7700 modules. So for those of you who are a little new to the 7K architecture, you have the M series line cards, which are the feature-rich, which are basically a full table. So you're talking about 1 million routing table entries, huge TCAM sizes on the modules, versus the F series modules, which typically are feature-rich modules with a streamlined capacity. So the actual capacity of each features in TCAM is smaller than the M series. That, however, has been different with the latest F3 module, where both these generations are going towards expanding and becoming identical and supporting both the feature set as well as the capacities that each other supports. From a perspective of FEX scalability, one of the questions you would have in mind is that, okay, I showed you a topology there with 2 parent switches and a whole bunch of FEXs. So how many are actually supported, right? So support for scalability of FEX depends on how many, how much RAM you have, how much CPU power you have, among other things. So if you can see the last column here, we have up to 64 FEXs that can be supported with the current generation of Nexus 2K, Nexus SUP 2E supervisors. So that's about 64 FEXs and a total of around 3,000 ports, 3,072 ports that you can add with using the FEX architecture. That's a whole lot of number of ports for a very dense environment. This table here, again a reference, I wouldn't expect anyone to remember this off the top of your head, but there is a reference of what line cards exist and what line cards do support FEXs. As you can see, most of the line cards do support FEXs already. The M3, which is one of the latest released line cards, will support FEX in the future. At this point, it's not yet there, but eventually with newer software releases, FEX will start getting supported down the line as well. Moving on to the Nexus 9K, there's the Nexus 9500. There's a whole lot of features and a whole different architecture with VXLAN, whole lot of things that the Nexus 9K brings on the table. The 9500 is the modular platform which brings with us FEX support as well. As you can see, we have support for 32 FEXs on the Nexus 9500 with the SUP A and SUP B. Then we also have individual line cards. Now, there are more and more line cards that start supporting FEXs, as the newer releases come by. So this is a quick sample of what is supported today. But as you verify your release notes, you'll see that more and more 9500 line cards start supporting FEXs. Well, this initial section of the presentation is going to be a little bit about data. I'm sure it's not the most interesting, but once we get done with what is supported, we will get into the most important part and the interesting part, where we'll discuss design and topologies. So this is about the 9500 and the 9300. So just the same way with the 9500, the 9300 also supports FEXs. Different models do support FEXs. There are some models today that don't yet support FEX. So the best place for you guys to get that information is from the documentation online about the release notes, the data sheets, and the config guides. All right, we touched on scalability just a little bit. So if you see the numbers here, you can understand, how many switches, how many FEXs are supported on each parent platform. And also depending on what kind of a deployment you have. Do you have an L2 deployment? Do you have a completely L3 only deployment? These numbers also slightly change. But in general, you can see that the numbers are, ballpark figure looks similar. All right, so that's as much as the introduction. Let me stop here for a second and see if there are any questions from the house.
I have one. If you get a FEX from scratch and you need to connect to a parent switch, is
Yep.
there any pre-configuration you need to do before you connect it, or is some sort of auto discovery that is instead of one?
Awesome, that's a very good question. So the question is, if I have Nexus 2300 or 2000 right out of the box, and I want to connect it to the parent, do I need to do anything on the Nexus? No. So for any configuration of the Nexus 2000, you cannot really connect to the Nexus 2000. No. So there is a HDMI console port, but that's not for configuration. That's just for diagnostics and internal information. So the moment you connect the uplink of the Nexus 2000 with the parent switch, provided you have a version that's supported and you're connecting it on supported ports, there are internal protocols, one called SDP, and a couple of other protocols which work in the backend and then bring that up online. So SDP is Satellite Discovery Protocol. So that's basically what runs between the FEX and the Nexus when you connect it to make sure that they discover each other. So it's automated. Yep.
I was advised, I'm still not clear, why we cannot connect a device that passes traffic on to the 2K, so another router.
Yeah, we have a section on that. So I'll probably hold this question until we're there. Okay. Awesome. So let's go forward and let me see. So I've got an LED light here up for grabs. So if you guys can just take a look at what we have here on screen, right? One of my challenges is when I look at a whole bunch of product IDs, generally they're all very cryptic, right? We don't call this we don't call this switch Nathan or Jeff, or that would have been nice, but unfortunately, it's like the car enthusiasts would know the Mercedes MP4-12C, but it's not a pretty name. Unfortunately, the switches are also named like that. And what I want, and I have a couple of giveaways here, is can somebody try to figure out what these numbers and letter combinations stand for?
Well, since it's on the slide.
Well,
Do I win because
unfortunately,
it's on the slide?
unfortunately, the PDF does not. Okay, at least for the gentleman who put his hand up to even try. You want to go ahead? He doesn't have the slide. Okay, first you said 32 ports. Okay, that's right here, 8 and 9. 32 data ports, okay. Can be 1 gig or 10 gig. What about the uplinks? 8, 10 gig, okay. 8, 10 gig uplink. What type of uplinks? SFP plus. Well, there's a whole lot of information you can get out of this name, and I can guarantee you 99% of us don't realize it when we look at the name. So if you take a quick look at the legend here, right? I have a breakdown of what each letter and number stands for, right? So whole bunch of information. Let's just break down the 2232 PP. So this is a Nexus 2000 switch, which is the N2K. And the chassis, meaning the Nexus 2000, it's a 2000. This number 7, the digit number 7 is a 2, which means it's a second generation FEX. So the first generation FEX was a 21XX. This is a second generation FEX, it's a 2232. The next two numbers, 32, as he rightly said, are the number of host ports. So it's a 32 port FEX. And PP also has a reference here. The first P refers to what kind of ports or what form factor of ports you have going downstream. And the next letter has the reference of what form factor of ports you have going upstream. So P is basically an SFP bar SFP plus kind of a port. So basically your 1 gig, 10 gig fiber interfaces. So this model is going to have 32 fiber ports going south and fiber ports going north as well. You can't find out how many there are from the name, but you have fiber ports going north. And the capacity of each of these are 10 gig. So you can find, it's a nice exercise to go through different models and try and figure out what each mean. So you don't have to go and ask somebody, you know that already. So with that in mind, there's a whole bunch of puzzle you can go through and try and figure out things. I'll leave that to you for later, but you can see the broad classification of the types of FEXs. So one category is the base T FEX, which is basically your copper interfaces. So you have RJ45 cables, you have 1 gig, you have 100 meg, 1 gig, and 10 gig FEXs. You can see the different generations all the way from the 22, 48, TP-E. You can see the 2232 TM-E. You can see the 2332 TQ. You can see the 2348 TQ and the TQE. So these are the most relevant, current relevant models that support your RJ45 based copper interfaces on the south, which is the host interfaces. So basically, when we talk about a FEX, there are two kinds of interfaces on the FEX. One is called the HIF, or the host interface, and the other is called the NIF, or network interface. Simply put, the network interface is what you connect towards the parent switch. So you can't really connect any host connections there, it's just for the uplink. And then there are the host ports that are used to connect to your hosts, your servers, and whatnot. Yeah.
Is the addition of the enhanced buffers, is that a new feature?
Yes, it is. It's there on all the third generation FEXs. It's there on a couple of second generation FEXs as well. We'll talk about it as we go through some of the models. Yeah, it's a good question. Yes, it is. Absolutely. So we'll talk about the blade FEXs. So the blade FEXs are an interesting type of a FEX. So all the FEXs you see in the other diagrams, they're all boxes that sit outside. You can see them on one of the tables near you. You'll see that they just sit on the rack by themselves. The blade FEX, however, is an interesting proposition where you don't want to run so many cables from your servers going to the host interface, where the FEX is now available in a form factor of a blade. So I'm sure people who manage a lot of UCS boxes or a lot of storage and other server farms, you'd have HP blade servers, you'd have maybe IBM from different vendors. So we support for about 4 vendors. We support HP, we support Dell, we support IBM and Fujitsu. They go on, yeah. So basically it's a blade, it's a network blade for the blade chassis. What happens is the servers internally connect to the network blade through the backplane, and the front of the blade switch has your connectivity going up to your 5600. Typically it's a 5600, but you could also connect it to a 9K or a 7K. So, there are models, but predominantly 10 gig, yeah. So as I said, we have a B22 HP. B22 is the name that corresponds to the blade form factor FEX. So you have the B22 HP, B22 IBM, B22 Dell, and B22 Fujitsu. And they have a different set of ports. One has 16, one has 8. The nice thing to note is that the servers actually connect internally. So the only cabling that goes out of these guys are the uplinks. Okay, it's a very interesting proposition. If you have a use case for it, it's definitely something that will make your connectivity and cabling much simpler. And when you already have a system for your servers that's designed to go in a blade modular chassis, this fits right in. It's a good question, and it's a good conversation as well. The only other thing that we did not touch upon so far is the SFP, SFP plus FEX. So typically, these are all SFP modules on the host interfaces. Almost all these FEXs have fiber-based uplink interfaces, right? So there isn't, most of the current ones only have fiber-based interfaces. What you need to do when you actually plan is to make sure that you get your distances for the cabling right, decide on what optics you want, find what optics are supported in each kind of interface, and then you're good to go. Yep. Well, yeah, that's a nice point, right? So TwinX, you have, so Cisco has a couple of fixed cabling options where you don't have a removable fiber and a SFP. What I mean here is that those are fixed connectivity options. So I do understand they're copper at some point, but those are for short length options, like just within the rack. So typically you don't have a direct RJ45 that goes to your uplink. So even the TwinX, you have some copper-based SFPs on both ends, and you have a copper cable attached, a direct attach. while they do use copper cables in between, they're not an RJ45 type regular base T. So they're all, the interfaces you have for the uplink are all SFP, SFP plus, or QSFP. All right? There's a superfluous information here that typically the uplink interfaces are at least as fast as the downlink in terms of the speed, the interface speed. So typically you would have maybe a 1 gig downlink or a 10 gig downlink. Your uplinks will be either a 10 gig or a 40 gig. So that's what our current generation FEXs have. So let me pause here again, see if you guys have any further questions. No? All right. What we'll do now is we'll just go over each category. We'll see what models exist for each category, and then we'll move on to the more interesting part, the design. So the first category is the 100 meg bar 1 gig base T models. The base T is obviously your RJ45 or copper-based interfaces. So the 2224 and 2248 TP are the oldest of the lot. So while they do support the same number of interfaces, the 48 port model supports 48 1 gig downlink interfaces. The catch is that they are an older model which support only 8 MB of buffer. So we'll talk about why buffer is important in a couple of slides that go down the line. The FEX that you must be interested in at this point, and the current one, the most relevant one, is the last one, the 2248 TP-E. So if anyone can tell me what that -E without going back to your slides, I think I can give out something else as well. Enhanced. Okay, I think I heard you first.
Oh, thank you.
So yeah, so the -E is the enhanced FEX. So this particular FEX was designed with a couple of use cases in mind. It's intended for certain kind of workloads, and the best part about this FEX you need to understand is that it has the 32 MB buffer for the 48 ports. We'll take a look at it in detail when we come to that particular model. But in general, you have about 32 or 48 copper south ports, and then you have SFP plus based 10 gig uplinks. So that's your copper offering for 1 gig or 10 M. We then have the copper-based 1/10. So this is where you'll use 10 gig copper on your host interfaces. So you have the 2232 TM, the 2232 TME, the 2332 TQ, and the 2348 TQ bar TQE. Well, you can try and figure out what each of these mean, but the most important and relevant one out of these lot are going to be the 2332 TQ and 2348 TQ bar TQE. Okay. One obvious difference between these two and these two, you can see that they're different generation. So this is a second generation FEX, the 2232, whereas the 2300s, the 23 are the latest and the greatest version of the FEX we have currently. So the 32 supports 32 downlink ports, each at 10 gig base T. The 48 supports 48 ports downstream with 10 gig base T. We have a model called the TQE. In this case, the E model that we're talking about is a cost optimized model with the 48. So it's identical in features, and what it can support, you wouldn't find any difference when you configure it, but it's a cost optimized model which is going to be a little cheaper for you to buy as well. So that's the latest switch that we introduced that came out not more than a couple of months ago. So again, one of the things you also see as a big difference between the let me ask you guys this. What is the major difference you see between the first two and the last two?
Support for QSFP.
Awesome. Everyone's awake, and I'm so happy for that. We have SFP versus QSFP on the uplinks. That really makes a major shift in what you're going to use for connectivity. So this is a 10 gig uplink FEX, whereas the 2300s are typically a current generation 40 gig uplink towards your parent. So as workloads increase, you're going to find that that number is going to go up. So in the future, the kind of uplinks we expect are at least 40 gigs or 100 gigs, and the 2300s are right there. Any questions at this point? Great. So the last category here is the optics-based, FEXs. So we have 3 models here for, for look and tell. So you have the 2232 PP, the 2248 PQ, and the 2348 UPQ. So somebody from the back, I think I want to give out a selfie stick now. Any guesses for what the U in the UPQ is? Front row is not allowed for front couple of rows. Yes? I think I saw your hand go up first. No? Unified port. Awesome. Can you pass this out for me? So the 2348 UPQ is a very unique FEX. It's our first FEX that supports the unified ports. So the 5500, 5600 has been supporting unified storage and Ethernet on the same box for a while now. So in conjunction with that, we also let you guys have the same capability over a FEX as well. And the 2348 UPQ is probably the FEX we'll talk about the most in the whole of the session. So that's another 32 MB buffer FEX, which is pretty much unique in the unified port capability. This is how it looks, and I'm pretty sure there's one of these boxes on the tables here. I do genuinely encourage anyone interested to, even after the session, take a look at these switches and really see how it looks and what it has got. You can see 48 ports on the front panel. So these 48 ports represent the host interfaces, the ones you see marked in orange. And then you can see the last section here has 6 ports. And those are QSFP ports. So typically you can use a QSFP at a 40 gig there, or you can break that down if you don't have uplinks, your parent with 40 gig ports, you can break that down into 10 gig ports and use them as 10 gig. So you have an option of 40/10 for the uplinks and 10/1 for your host interfaces.
Do all of them support dual power supplies or only the 2348?
Good question. All our FEXs support dual power supplies, one-on-one redundancy. We'll look at that in one of these slides. So we have the fan modules and dual power supplies at one-to-one redundancy, and this is for all of them. So, sure.
I mean, the last time I touched those, what you had to do was you kind of had to allocate a fixed number of ports to say I'm going to be fiber channel,
yep.
and they had to be contiguous,
yep.
and you couldn't change them without a reload.
Yep.
Is that the case with the FEX?
Yes, it is.
Okay.
So for fiber channel ports, you need a reload. There is a slide with everything around the fiber channel, how you would configure it, and what are the guidelines. But to answer your question, yes, you need a reload. Yes, there are certain rules. Well, we're in a casino; there have to be rules. So there are rules of which ports you can use, odd, even, and hey, even have an odd even form on the FC ports. So we'll come to that in the FC section where we'll show you how to configure fiber channel on the FEX. So that's how the 2348 looks, and that's everything about the FEX here. So the fundamental point about buffers here is that before we even discuss buffers, one thing we want to understand, and this is the second major takeaway I would like for you guys to have, even if everything else is details that you've forgotten. FEX is really an extension module. So FEX is intended for a low-cost, high-density server farm or connectivity option, right? You want to use that where you have a huge number of servers, not necessarily all being top-of-the-line servers, but you have a whole bunch of servers. Now, imagine if you had 150 servers, all of them had small workloads, not major, and you had to burn ports on the parent to connect to a FEX, right? That doesn't make sense. So typically, a FEX is intended for such a solution where you use your normal server ports. We've had certain specific applications which require a very high performance, or they have some very specific behavior in them. Certain applications are very bursty in nature. So in a span of a few microseconds, they'll send about 10 times the capacity of that interface, right? So if you have a 10 gig interface, across an entire second, you may be sending only 1 gig of data. But that 1 gig of data could have arrived in the first 10 milliseconds, right? So if you look at the speed in that 10 milliseconds, it's much beyond the 10 gig of that interface. So typically what happens is that there are buffer overruns that happen because of burstiness of applications. So that is one of the major areas where the bigger buffer spaces help. We have 32 gig buffer on a lot of our FEXs today, so each architecture is slightly different, but that's the current standard. So this 32 MB of buffer is divided up between ports in different ways. We'll look at that as well. The point, again, why it is important is to handle bursty applications and also to work with workloads with different speeds, right? So how many of you here have 100 meg devices in your network still? As you can see, that's a whole lot of people, right? So there's a huge disadvantage of having an uplink at 10 gig and your downlink at 100 M. So has somebody experienced this kind of a problem because of an uplink being at a very high speed and the downlink being at a very low speed? Can you just describe to everybody what is the actual challenge you face?
All right, so what happens is that the upstream switch can send data very, very quickly. So you send a burst of data at 10 gig. It's basically the reverse of sucking on a straw, right? You've got a big funnel of data. It only drips out at 10 meg, and particularly if you don't have a well-behaved TCP application where things will slow down, you end up blowing out the buffers because you're pouring all these flows down at 40 gig. You can only drain them at 100 meg a piece, and that stuff has got to go someplace. So to also follow up on an additional comment, I have Oracle servers. Oracle is very chatty on their internal interfaces. So we take Oracle servers, we connect the internal interfaces directly to the switch. The public interfaces that talk to the servers, we connect to FEXs. Just because of buffer management, traffic management, this is essential stuff this guy was talking about, is the workload. So the outer workload is far less than the inner workload. So we connect the outer connections to FEXs. Save the ports, inner connections go directly onto the switch. Because Oracle gets really mad when it misses the packet. It's sensitive.
Awesome. Can we have a mic for him here? I think you may as well do the rest of the session. I'm happy to sit and watch, really. So that's spot on to where the problem really lies, right? The straw analogy. You have a huge pipe coming in, and while the amount of traffic or the amount of water that comes through might not be millions of gallons, it comes in very fast, right? So you have a huge pipe which even if you're just sending maybe 1 gig of total throughput, it comes so fast, it comes faster than the downstream can actually drain it. So that's where you typically encounter a buffer overrun. So you have to store it somewhere, and you need buffers. So we have 32 MB buffers, but even if you had 320 MB buffers, I can guarantee you that if you burst long enough, you can still make that drop. So there's a number somewhere, and the number we have is 32 MB. We'll take a look at what scenarios that you might run into these buffer overruns a little later. So a quick difference of the internal architecture. I'm sure you would never really look at it this way outside of this session, but for you guys to understand what's on the table in each of these, the third generation FEX there, the 2300, we have a single block ASIC, which pretty much is the, does everything there. We don't have multiple ASICs or multiple ingress components. We do have the buffer in 2 different blocks, but they don't make a difference because that 32 MB buffer is available for all the ports. So in comparison with the older 2248 PQ, you can see that the uplinks and the ASICs that control the front panel ports, they're separate, okay? So there's only a particular way that each of these ports can go through, and that also results in only a particular set of the buffers they can access, right? You don't need to know all of this, but the fundamental fact here is that with the 2300s, which is the latest generation FEXs, the buffer is more, and it's also more intelligent. So the way we carve the buffers and the way we work with the buffers for the host interfaces down south and the north, the NIF interfaces is much better and enhanced in the 2300 generation. So you can configure, just a preview that you can actually configure any of these ports on the 2300, maybe one of the host ports to use up all the 32 MB buffer if you need, right? It's really not recommended, and it's a really bad thing to do. But if you wanted to, you have the ability to control that. So you can basically say that port number 10 on the host interface is something that's so super chatty that I want it to be able to use all the 32 MB buffer if it needs to, right? So that's the level of control you have with the 2300s. Now, there is a small disclaimer here. So with all of the 2300 FEXs, you have 40 gig uplinks and you have 6 ports. So you can connect up to 6 into 40 gigs for your uplinks, right? 6 into 40 gig uplinks. Now that is true when you are using those ports as native 40 gig ports. So if you have a QSFP 40 gig port on the other end, maybe a Nexus 7700 or a Nexus 5600, then you're good to go. You have a total of 240 gig uplink bandwidth. But you also have the option of using a breakout cable, one QSFP breakout on one end, one QSFP port on one end at 40 gig, and 4 individual SFP plus breakout options on the other end. You can do this, but there is a small limitation that when you're using a port channel towards the parent, the maximum number of such ports you can have at 10 gig are only 8. So the best way to run the 2300s is to use 40 gig. If you do have an option of using 40 gig on the 2300s, that is the recommended way to do it. You can still run it at 10 gig for extremely small workloads. You may not see a problem, but the total maximum bandwidth on the uplink that can be supported with 10 gig is going to be 10 into 8 versus 6 into 40 with the 40 gig ports. All right. This is a quick slide reminding you guys of how the 2348 UPQ is actually different from the other models. So it's interesting to note that the uplink for the QSFP plus module is one of the unique factors, and also the fact that we can do fiber channel on the downstream. So the 2232 PP and the 48 PQ are the closest, identical models, but the differences are obvious. So this is the 2348 UPQ is really your choice of FEX if you need. That's the only choice for FEX if you need a unified FEX, or if you need anything with a decent amount of traffic throughput, and you want the 32 MB buffers, and you have fiber-based interfaces. This is your FEX. The 2348 TQE is the 48 port equivalent, except that it's a copper based model. So we're really talking about 10G base T. So I know that generally in kinds of deployments, the copper 10 gig is actually a little more power consuming than the fiber. So while it's not all that common, there still are a huge number of people who deploy it. So here's the option where you can use an RJ45 based 10 gig base T in the 2348 TQ. Okay. Every other thing is very similar. The internal ASIC is the same between the UPQ, the 48 TQE, and so is the option that you can only do 8 into 10G uplinks. Okay. That limitation of maximum 8 ports for 10G holds true for all Nexus 2300s. The 48 UPQ, the 48 TQ or TQE, and the 32 TQ. All right. Let me stop here for a second and let you guys read that, or any questions I'm happy to take. Great. Yep.
Does the 2348 TQ-E doesn't support BIDA connections?
No, they're just, so, yep, yeah, they do. BIDA is definitely supported on the upstream. So the next FEX, and I would say that this is the last FEX that we're going to talk about in this much detail, the most relevant one, is the 2248 TPE. So quick check, what generation is this FEX? Second generation, great. But why are we still talking about the second generation FEX here? The reason is this is the latest or the last of the 2200 FEXs. And this was built for a very specific, request that we had from a lot of customers who had high performance, big data kind of environments. So while most of the previous 2200 FEXs had about 8 MB buffer, this is one of the first, 32 MB buffer FEX. It's not the third generation ASIC, but we still have 32 MB FEX, 32 MB buffer. And one of the definite FEX options, if you have like very slow traffic, like 10 Mbps connections or 100 meg, a huge amount of 10 or 100 meg ports that you need to connect to. So this is also Cloudera certified, and the way we do the 32 MB buffer carving is slightly different from the third gen FEX, but we still do have the 32 MB available. And it's the typical FEX of choice if you have 10 Mbps connections. Again, those are dwindling and those are definitely legacy devices, but this is one of the few FEXs that supports 10 Mbps full duplex only. Again, those have to be legacy environments. You would not want to connect them elsewhere, and that's why the 2248 TPE is still relevant. Sure.
On the 2 series, the second generation, just for port 1 to talk to port 5, it had to go all the way back to the Nexus switch.
Yep.
Is the third generation smart enough to switch between those 2 ports?
It's a very good question. So none of the FEXs, including the 2300, support local switching. One of the reasons so we basically send the package towards the parent. So while we do send the forwarding lookup that needs to happen, we'll go through that in a little bit where we look at the actual structure of the header that's put in, but the answer is that we don't have local switching on the 2200s or the 2300s. That's depending on the kind of positioning for where we want the FEX to operate, what is the kind of requirements. Generally, from a lookup perspective, even when you have a huge number of scale for the FEXs, it doesn't really bog the parent down on the number of lookups. So earlier when we were talking about scale, the scale of the FEX depends on the CPU and the RAM of the parent, not about how much hardware, data plane flows it can support. So while all of these FEXs still go to the parent for processing of the packet, it does not really impose any kind of a overload on the lookup at the parent level. Yeah.
I'll just add something because I was obsessing about this and somebody kind of reminded me. The speed of the backplane of a Nexus 7000 first generation is 80 gig.
Right.
So it's 2 uplinks. So from the standpoint of,
Absolutely.
People obsess about going between 2 line cards on a Nexus 7K, and that could go faster.
Yep.
And then I thought, okay,
Absolutely. Well, you talked about the first gen Nexus 7000. I can tell you the same holds true for even one of the middle generations of Catalyst 6500, right? So in general, hardware switching is really built so fast that I've worked for 6 years in TAC, and there's not even once where I saw a scenario where the forwarding engine is overwhelmed, right? You might fill up links, you might fill up buffers. I've never seen one situation where you fill up the forwarding lookup capacity because it's so damn fast, right? You can do millions of packets lookup per second, and most of the times, as soon as you're done looking up thousands of packets, those packets actually have to go along the link, and that's a bigger bottleneck than the actual lookup itself. So that's how hardware switching works, and that's how it's been from the days of the Catalyst 6500. Okay, so the 2232 PP, I'm going to leave this slide for reference. Again, this is an older generation, second gen FEX with the SFP options. Similarly, the 2232 TME. These slides are here for reference. Quick note on the TME. So the difference is that it's an enhanced FEX from a few points, that it's got a better power and latency characteristics than the older one, the 2232 TM. So if you were looking for one of these, the TME is definitely the better choice. The reason for that is that the internal PHY that we use on the front panel port is more power efficient. So I'll give you a quick note here to see what the difference really is, right? So the first one is the 2232 TM, and the second one is the TME. So this is the TM and this is the TME. So you can see that there's a power difference of around 2 watts per port on the PHY side. And the latency at the transceiver is also slightly better. Okay. We'll now quickly take a look at the power and the fan cooling structures. Now, there's only so much you need to know. It's not a complicated modular chassis. So we have a redundant, 1:1 redundant power supply. So if one fails, the other takes over. So those are options that are fixed. And you can see that the power supplies are on either side of the FEX. And you can see the fan modules in the center. So you have N+1 fan modules, right? An interesting thing here to note is that you have blue and red labeled fan modules, right? So can some of you guys tell me if we even have a particular red handled fan tray in any of the switches on the tables? Question is, any red handles on the fan tray in the Nexus? All blue? Okay, so that's the default, right? So what that really means is the direction of airflow. So you have the choice of choosing either hot exhaust on the port side or hot exhaust on the reverse on the reverse backside. So basically, the blue means that your hot air is going to be coming out of the port side, whereas the red one means that the hot air is going to be going out of the backside. So that depends on if you have a cool aisle or a hot aisle kind of a deployment in your rack. So depending on what you decide to buy, you want to make sure that what you have is in line with what you purchase here. So if you have a hot aisle, then you make sure you buy the appropriate one. Just a quick schematic showing you where the cold and hot air exits are.
If a customer bought the wrong one, is it just the power supplies and the fans they need to swap?
It's just the fan.
So the internal of the Nexus 2K is the same?
Yeah, absolutely. It's just the fan, actually, not even the power supply.
No, they have two part numbers for fan or power supply. The part and then the process.
They need to match. If they don't match,
Let me get back to you on the, I'm talking about the 2300s. Okay, I'm talking about the 2300s. If you have a specific PID in mind, we can definitely check that. Okay, so.
Another question I have for you is, on the 2348Ts with the DC power supply, why does it come with a C14, C15 power supply?
I will really have to check that with. So you mean that was ordered here in America? Yeah. Okay. We'll have to take that offline. We'll probably see what is the specific issue you had, because from what I know, the standard is not. We'll take that offline. Okay.
What would happen if you carelessly mixed red amongst the fans?
See, what will happen is you will not see an immediate warning or an issue, right? But what is going to happen is if you have a hot aisle, so the center of the aisle is where all your heat is going to be. So that's where your cooling is going to be, right? So if one model was flipped and it was put on the other side, you're going to have no cooling on the other side, right? So you're going to start feeding it. So one exhaust, so your nearby switch will have a hot exhaust, whereas this one will have a cool intake. So instead of getting cool air from the front, it will actually get hot air. You're going to see the temperatures rise. It's not going to pop up an immediate warning, but if you operate it that way for extended periods of time, you might have an issue with a hardware failure some point. Again, there won't be an exact error message per se. And it's very unlikely one FEX is going to affect the temperature of your entire system. I'm pretty sure of that. But if you have a continuous hot intake, you might run into problems. Okay, so that was as much about talking about the FEXs themselves, right? A lot of interesting questions coming up. Anything else before we move on to architecture and a packet walk? All right, we're good. Let's now go into the FEX. Let's see, what the packet walk looks like. What is the forwarding methodology inside the FEX? How the packet actually goes through it. And then we'll also take a good amount of deep dive on each of the features. So basically, what is supported on the FEX? What are the different combination of features? What do you need? Which FEX supports it? We'll finish up with this section, and then we'll go to the most interesting part, which is the topologies and the design. So what kind of a design is supported? How does it interop with VPC? And a good, interesting section coming up right after this. So I'll just wait for a moment for you guys to, take a quick look at this and let it sink in. So what you see here on the diagram is you see an ingress Nexus 2000 FEX here. This is where the packet comes in on. And then you have another Nexus 2000, which is where the packet is supposed to go out of. And you see the parent in between, Nexus 5000 or 6000 in this example. Now the ingress UPC and egress UPC basically stand for the Unified Port Controller. It's the ASIC that actually parses the packets and processes it on the Nexus 5600. So let's do a quick packet walk of a packet that arrives in here and then exits out of the Nexus. The first step you see happening is that the frame is received on the N2K HIF port, right, on the host interface. This is going to be a traditional Ethernet packet, right, and there's nothing fancy going on there. It's just a normal packet with just the same headers that your server sent it. What the Nexus 2K will do is, first thing at the port level, it will parse the frame, collect a whole bunch of info from the packet, at the L2 level, at the L3 header level, put all of this information into something we call a VN tag, okay, and attach this VN tag to that packet, and then ship it off towards the Nexus 5K. All right, just to repeat myself, packet comes in, headers are read by the Nexus 2K, a VN tag or a special tag called the VN tag is generated with all the information from the headers that's put onto the packet and then shipped towards the Nexus 5K. Why do we need to do this? Have any of you thought of why do we need to do this? Why can't the 2K just send the packet directly to the 5K?
The main switch has got, well, since all the kind of brains are in the main switch, so in the MAC table, like MAC learning and everything else, the main switch has got to know what port that thing has come on, and it's a line card. So
Absolutely.
no brains.
Absolutely. On a normal switch, when the packet comes in, well, the IP header and the layer 3, layer 2 header have most of the information required, right? But when the CPU sees that packet, how is it expected to know which port it arrived on? The FEX has, if the FEX is connected to the parent by one port on the parent, for the parent it's just one port, right? So if you have 48 ports on the FEX, packets from all the 48 ports are just going to arrive on the same single port on the parent, right? How does the parent actually differentiate between each of this? One of them is in one VLAN, one of them has a different QoS policy, one of them has a different feature configured. You need all this differentiation. So there comes the concept of a virtual interface. Okay? So basically the VN tag is a virtualization tag where in addition to the packet, a whole lot of information of the WIF or the virtual interface, the source virtual interface, the destination virtual interface, and a whole bunch of other things are put into the VN tag and sent. Now, on the step number 3 here, when that packet is received on the ingress UPC, the ingress UPC reads this information, processes, digests that information, and strips off the VN tag. Then it looks at that information and makes its decision just as a normal switch would, and then it sends it out. Now, in case that the destination is a regular parent port, there is no more VN tag. It just sends it on the regular parent port. But in our example, the destination port is across a FEX. So what it will do is it will regenerate the VN tag for the new information after the lookup. So that information will have both the source WIF. It will also have something which is more important, the destination WIF. Okay? Destination WIF is a destination virtual interface. It puts that information and sends it to the FEX. Now, all the FEX is going to do for that packet is read the VN tag, see what is the destination WIF interface, the DWIF. With that, it knows which of its local port it has to send the packet out on. There are a few features which are offloaded to the FEX, like queuing and all that is done on the FEX. The FEX will do that locally, and then it will send it out on the destination port. It's very important for us to understand this as it goes on, and also the fact where where the decision happens. So yes.
How big is the VN tag? Does it affect the packet size if the host can send?
It's pretty small. It's about 6. It's about 6 bytes. You can see it here. It's about 6 bytes long, So while yes, 6 bytes is a considerable amount for a small packet, it doesn't really affect it too much. 6 bytes is typically small header. Another, since you brought that up, another interesting thing to understand is typically a lot of our policing and QoS policing that's done keeps track of packet rates. Typically, these parts of the headers are excluded. So it's generally only the typical IP header or the L2 header from where we start looking and counting for the policing. So even if you had something extra, those are really not counted. Okay. So we all know what a VN tag is and we know why it is used. Now, can anyone think of a use for VN tag? And I would definitely now keep the first row off because I think you've got quite a lot of answers already. One quick question here to see if, has anyone encountered a situation where you use a VN tag but you don't necessarily have a FEX? So the question is, have any of you encountered a situation where you need a VN tag, but you don't necessarily have something like a FEX? It is an encapsulation of sorts. It's added on the header, but my question is, where would you need something like that if you did not necessarily have a FEX? Into a server. That's really a very good point, that your server might have one NIC interface, but you may be able to virtualize beyond that one interface as well. So there are many situations in which servers also understand VN tags. Okay? Your servers can also understand VN tags, and based on that, you can send VN tags to your ESX host, right? So when you have a virtual switch inside your ESX box or UCS host, you can actually send VN tag packets to it, and then the internal virtual switch on the server will take care of redirecting it appropriately to each server. So you can actually have a VN tag go to a different system, not necessarily a FEX, but that's one of the use cases. Another reference slide for you to understand what all exists in the VN tag and where it exists on the frame. Guys, understand that this is local between the Nexus 2000 and the parent only. So if you're only talking about between these two, it's only going to exist on between the FEX and the parent. Except for that use case I mentioned, in typical non-virtualized VN tag use cases, the VN tag is never sent out. Okay. Now, coming on to port channels on the Nexus 2K, you can actually have a port channel built from the FEX front host. So you can take 3 or 4 HIF interfaces on the FEX, you can bundle them up together and make a port channel out of it. Now, the interesting thing is that for the parent, that looks like one interface. So the port channel going from your FEX HIF is just one interface for the parent. The parent just puts one LIF information there, one WIF information there, and sends it to the FEX. When the FEX receives it, it knows that it's not one interface, but actually 4 in this case. There's a hashing that's done at the FEX level, which then redistributes that packet to the local port channel members. Now, what this does is that there is, since every interface has to have a WIF information, like a virtualized interface information, here you not only do you have virtualized information for each port, you also need another one for the port channel as well. So we'll talk about resources, and we'll talk about an interesting feature that we have in VPCs with FEXs in a little while. Then we have the option, so in some of these platforms, right, we have the option of pinning a particular host interface to a very specific network interface. In a typical scenario, we see most of our deployments in typical scenarios involve a port channel going towards the parent and host interfaces going south. So this example is just that. So if you can see here, the northbound interfaces are a port channel, and the southbound interfaces connect to hash between the port channel members. What's the advantage of having a port channel going towards the parent? Yep. Bandwidth?
It's how it segments the front of the switch. If you do 2 links, it cuts the switch in
Absolutely. So port channel gives you resiliency of failures of links. It takes care of automatically hashing between the host and the host interfaces and the uplink interfaces. You don't have to manually touch anything, right? So the best way to do use FEX is to use port channels on the uplink. But there exist a few cases where you might want to do a static pinning. So dynamic pinning is basically the option where you use a port channel where which host interface is pinned to which network interface is actually dynamic, and it's taken care of by the system. As opposed to that, you can have something called a static pinning. Okay, static pinning is where you statically assign one group or one block of ports to one network interface, and say that that's just as much as it's going to be, right? So this set of ports will always go to that network interface. So if that particular network interface fails, that group of your host interfaces will actually be down. Is there a use case where you can actually use static pinning? So there are some deployments in servers where you will have an active standby NIC configuration on the server, right? You need an active and a standby. The server cannot do a port channel, okay? So it's got two NICs, but it can have only one active at a time. So how many ports are you burning on the switch whenever you do that? You're burning 2 ports. You have to have redundancy. So typically, in this example, your active NIC will connect to here, and your standby NIC will connect to here. And if that's the norm in your network, you have 48 servers with 24 active interfaces and 24 passive interfaces which are not in standby. You don't really have anything coming through them. Think about the situation here that if you had a port channel with those 48 ports and versus 24 ports, your oversubscription is never fixed. So if a port goes down, the oversubscription can change dynamically, and your application might not see the same kind of performance, or it'll see a change, right? So if you have the active standby NIC configuration, the nice way to do it is connect all the actives to one block or one NIF or one set of NIFs, and similarly all the standbys to the other set of NIF. So if one uplink goes down, all the servers that have connectivity to that uplink, their active interfaces will go down, the servers will fail over to the standby, and you still are up with the exact same oversubscription ratio. Nothing changes in your oversubscription. So that's one of the niche use cases where you might want to do static pinning. We do support storage technologies on the FEX. So FCOE is where you can carry fiber channel traffic encapsulated over Ethernet. That's supported in quite a few of our FEXs. And then the 2348 UPQ supports native FC on the FEX itself. We have a detailed slide later about the details and the specifics, but we do support FCOE and unified ports on the FEX. Span, this is one of the questions that gets asked quite a lot. So FEX ports can actually be span sources, but they can't be span destinations in general across most platforms. So you can span a port on the FEX HIF that can be a source, but you cannot actually send traffic towards your monitoring device. That does not also make sense because typically a span destination carries a lot of traffic. You do not want to overburden your other devices on the FEX just because of your span destination traffic. So we don't allow that as well. Yeah.
What about using our span coming out through a FEX?
You can do that. So that's not span traffic, that's just data traffic, right? So RSpan or ERSpan traffic on the network is going to be normal traffic, so that's okay. Your source is elsewhere, but it can go through the FEX, it won't see any difference. So just to recollect again, so span source on the FEX is possible, span destination on the FEX cannot be done. Okay. There are a few limitations with the 7K F2 line cards. They cannot do a span with the FEX. The F2E can do, F2 cannot. So again, as I said, for all specific matrix combinations, go to the specific document, specific release, and make sure that what you want is actually available on that release and that platform. Okay, here's the interesting part. Now, we talked so much about the 32 MB buffers, right? But how does it actually work? How does it managed? What is the default? So how the buffers are organized on the Nexus 2K is that typically the direction of the traffic matters. Okay, we generally have two directions. There's a name that we use for the forward and the reverse direction. We say H to N or N to H. The simple understanding of that is network to host or host to network. So if you are trying to troubleshoot a scenario with packet drops or something, the first thing you want to understand is which is the direction that has the drop. It's relevant because each direction is managed internally in a different way. So H to N versus N to H have different queuing structures internally. What happens is there's a particular amount of fixed buffer that each port has, and then there is a maximum buffer that it can eat up to. That maximum buffer is called the queue limit. So if you see this example here, you can see hardware, the model number, queue limit. So queue limit is the absolute maximum that a port can actually eat into. So if you have a bursty application, you may want to give that bursty application higher preference, but that will come at the cost of some of the other ports. So all these tweaks are available to you if you want to do that, but if you assign 32 MB buffers to just one port, it's almost a sure shot way of making sure you'll have drops on other ports. Yep. I'm sorry, could you repeat that?
Where would you be able to see those drops that cause
Buffers. That's a very good question. The place where you look at it is in the show queuing interface. So when you do show queuing interface and then the FEX interface number, you'll see drops. So different generations of FEXs have had different supports for these counters. The 2300s and the 2248 TPEs are ones with the maximum number of counters available. So ideally, the place to catch those drops are at the show queuing interface. Yeah, they will show drops as well, but how much visibility you have it varies. Like the 2248 TPE will give you class-based counters, so to tell you which port, which class dropped the counter, but the 2232 will only have a per port counter. So.
I thought you couldn't do QoS on a 2232.
You can play with the queue limits. So queuing, when you say you can't do QoS, queuing is inherently there. Whether you configure it or not, queuing will happen. So the queuing is already there. Without queuing and buffer sharing, it won't work. So even if you haven't configured anything, there is QoS queuing happening already on the FEX.
So, but in the case of, let's say I had and I forgot which of the 15 kind of queuing mechanisms, but I have a priority queue and I have non-priority queues.
Yep.
That transmission for that particular port, that decision as to this packet goes first and this packet goes second is done at the 5K at the parent switch, not done at the FEX.
No. So the queuing is always at the FEX. Queuing is always at the FEX, right? So the processing, if it's a CPU packet, if it's a processing of the packet on the parent, when it's received there, that's done by the parent. But at the FEX level, for all the packets that come in and go out on the NIF, that is still controlled. That queuing is still controlled by the FEX. So we'll talk about offload in a little bit. That should also help answer your question.
We were told by the TAC, or maybe it was a voice expert or something, to put all of our, even though they're 100 meg, our voice gateways on the Nexus because we couldn't do true QoS on our 2248.
You can, so when you say that, so with QoS, you want to be specific about what kind of QoS you're talking about, right? Do you want to tweak your queuing? Do you want to tweak your, your scheduling? Do you want to change your policer configuration? Queuing is already there. So what we will be able to, will you be able to add another user queue? Will you be able to do a custom QoS? Maybe not. Queuing is anyway already there. So.
How many queues, how many hardware queues are on FEX?
So we have about 8 queues.
8 queues.
Yep.
Cisco expanded the definition of QoS with Nexus, so it's not just using the DSCP or concept anymore.
It's
QoS is now involved the actual input-output queues and all these.
so
Plus all that stuff, and I don't, it's confusing if you're
the point is to be specific about which part of QoS are you talking about. Are you talking about the queuing? Queuing will have to happen because there's no forwarding without the queuing structure. So in the interest of time, the QoS section, I can guarantee you that we can talk about it for hours at length for the 2K. I'm happy to do that right after the session. We're running a little behind time, so any of these QoS questions, I'm happy to take it right after the session. Yeah, you had a question?
I was just going to say, would it be safe to say that the Nexus 2000 does not mark the packets as far as class of service?
No, it does. It does. We can offload the ACL on the FEX as well. We'll come to that. Right there. So while the forwarding decision is actually taken by the parent, right? The parent does the forwarding decision. A whole bunch of stuff can actually be offloaded to the FEX so as to conserve resources of the CPU on the parent. While I said it has a limitless hardware forwarding capability, CPU is still going to be reserved. So a whole bunch of things we can actually do on the FEX itself. The additional thing is QoS, some of the ACL and some of the TCAM resources on the parent can also be moved to the FEX for offloading its own QoS policies, right? So all these things that you see here are the CDP, the LLDP, LACP, DCBX are processed by the FEX's CPU, and the QoS can be offloaded to the TCAM on the FEX. So depending on what kind of a QoS policy you're configuring, some things might not be compatible. When that happens, it throws an error message and it configures it on the parent. However, if it's supported, it actually takes it and it configures it on the FEX. The QoS offload alone is disabled. You need to turn that on if you need it. Okay. Almost all current FEXs do support QoS offload. Is there a question? Now, a gentleman was asking me a question about, connecting other devices to a FEX, right? Fundamentally, we want to understand what a FEX is meant for, right? FEX is ideally meant for host connectivity, right? You have a server farm, you have a huge number of servers, physical servers, virtualized servers, you have, server racks with actual full boxes, you have blade servers. Those are the ideal, things that you intend to connect to the FEX. The FEX has a BPDU guard on by default, and it's enhanced by a BPDU filter as well. You may be able to turn off BPDU filter. You cannot turn off BPDU guard. So if you connect a switch to the FEX, what's going to happen is that you're going to put that port into BPDU error disabled state, right? You may actually filter on the other switch, right? Maybe whatever switch you're connecting, you could technically, put a BPDU filter on it and make sure it doesn't send BPDUs, right? That link will be up and that switch will work, your traffic will go through, but it's really not a recommended way of doing it. If you have multiple interfaces, it means that you're running without spanning tree and you're bound to have loops. So connecting a switch behind a FEX is ideally discouraged. A FEX is typically intended for host connectivity. The next interesting thing is, okay, not a switch, how about a router? Right? So the challenge with routers is that a routing protocol, as you were just saying, needs support for your queuing, right? Your queuing needs to be supported at the interface level. The reason this is important is because control traffic has to be prioritized over other traffic. So maybe you have EIGRP running from a router and it's trying to build neighborship with your parent. That traffic does not get prioritized, then that's not the way you want to run your routing protocol. So currently only the Nexus 7000 supports connecting a router to the FEX. The 5K and the 9K do not support connecting a router to the FEX. Again, guys, the general guideline is that the only scenario where you would want to do this is if you have some kind of a legacy device that you just have to attach. It doesn't have a whole lot of traffic. It's not super critical. You just want to have routing neighborship because that device needs it, right? So that's the only scenario you would want to use the FEX for router connectivity. Imagine if your router is actually one of the most critical parts of your network. You do not want to connect it behind an O-subscribed device, which is intended for server connectivity.
I also heard a while ago that if it was static routes, the router connects that's just fine, but if you're running the IGRP, not to do that because of the multicast stuff.
For the 5K and 9K, it is. Yeah.
And so that also includes things like mainframes and things that happen to run OSPF.
Correct.
use of the term router is not necessarily a Cisco device.
Absolutely,
It's
absolutely.
anything that runs OSPF or RIP or...
Absolutely. Firewalls are also other examples. I've had a couple of people ask me if I can connect a firewall. Well, technically you can. With the 7K you can, and it'll work. Do you want to? It depends on how critical it is. If it's really a very critical device, typically routers aggregate and send traffic north, right? So the higher the amount of traffic you're trying to pump through a FEX, the more the reason you want to move it to a parent. And this is particularly true because if you drop a few packets for a data stream, all that is affected is that particular flow. If you drop those few control plane traffic packets next to next, what goes down is your neighborship. That means your entire site is down, potentially, right? So in the interest of time, this is how a typical converged infrastructure looks like. Especially with the 5600s, you have FC traffic, you have Ethernet traffic, you have FCOE traffic, and the ideal boxes you're talking about here are the 2348 UPQ, as well as your blade fabric extenders. So you have a wide and rich variety of connectivity options where you can carry FCOE traffic over Ethernet, you can carry native Ethernet traffic, you can also do FC on the 2348 UPQ. So from a feature update point of view, FCOE over FEX over the F3 line card was recently introduced in 730. So before about 4 months, if you had a FEX connected to an F3 line card, you couldn't do FCOE over that combination. But we did introduce both FCOE over FEX over F3 and FCOE support for VPC, FEX VPC in 7.3. So these are minor updates, minor features which we start enabling as we go down the line. So big reference slide I want to leave you with for understanding how and what options exist for using FC on a FEX. So we've been talking about it for so long. The FC option with the 2348 UPQ is available using the 5600 parent. So when you have the 5600 and the 2348 UPQ, you can actually use up to 16 gig FC interfaces on the front panel ports. There are a few limitations. They have to be on odd number ports. And you can do 2, 4, 8, or 16 gig FC on the 2348. The 2348 supports F-type ports. NPV ports have to be connected directly to the parent. All of this information is definitely available on the config guides, and the guidelines are very clearly listed out. It's just for a reference to let you know that this is supported, what is supported. Yep.
Do you know why the limitation of 5600 as a parent switch for this is silicon, or is it just
So there are a couple of reasons. The 5600 is built to have more number of 40 gig ports, and the 5600 is typically the one with a high amount of buffers. So you have about 25 MB buffer for a set of 4 ports on the 5600. So when you're talking about FC traffic, FC is typically non-drop classes. When you say there is a non-drop traffic, it means that you need to have enough buffers to make sure you don't drop. So that's one of the reasons why 5600 is the targeted platform. Keeping that in mind, we've also built it that way that only the 5600 supports it. Moving on from FC, everyone's talking about ACI. While this is a very chatty, very a lot of stuff going on in this slide, the point I would like you to focus on is here. You might have a combination of other devices here. You might have Nexus 9Ks with FEXs connected. You can configure and roll out FEXs through ACI. So there's a small snippet that I have in the end where you can see how it's done. So does FEX work with ACI? Yes, it does. There are specific compatibility guidelines, but FEX does definitely work with ACI. All right, so we've covered a whole bunch of features and what the FEX can do, what it cannot do. We'll talk a little bit about design, right? One quick show of hands I want to check with you guys is, how many of you here work with VPC? Wow. So VPC is, just to give you an example, 6 months ago in Berlin, VPC is one of the oldest technologies, right? We had VPC from close to day one for Nexus 7K, and it's been there forever. Right? And we had a session on VPC in Berlin, and while other sessions got 100, 150 people sign up, VPC session got close to 500 people who signed up for it. So while it's still one of the oldest technologies we have, it's also the most deployed. So keeping that in mind, we will look at FEXs, FEX connectivity options with a good amount of focus on VPC. So the first section we will talk about here is designs, basic designs which you can do. There's no specific reason why you should do one over the other at this point, but we'll come to the VPC section in a bit. This is the simplest design. So there is no VPC here on the south layers here. So even though you see a VPC here, the connectivity is not that way. This is a typical design where you have your hosts, UCS or any of your hosts, that connect to a FEX. The FEX is then aggregated with a Nexus 5000. The Nexus 5000 is in turn connected with the 7K. Okay? In this architecture, you see that while the FEX has multiple uplinks and there's a port channel there for connectivity, if you have a single FEX failure or a 5600 failure or a single 7K failure, you don't really have redundancy there. While technically this is possible, so this is called a single-homed Nexus, single-homed FEX attached host. So it's single-homed everywhere. It's not a very pretty design, which is why very, very few people actually choose to do this. The next brings one layer of redundancy to this to the table. Between the Nexus 7000 and the Nexus 5000, you have a VPC running here. So I want to give away something for somebody who can tell me what does this, what kind of a VPC is this between the Nexus 7000 and 5000? So I'll repeat the question. Just don't bother about the FEX. Just remove this from the picture right now. Between the Nexus 7000 and 5000, I've shown this 4 links cross-connected VPC, right? There's a special name to that kind of a VPC. Yes? That's not enhanced VPC. VPC plus, no. It is a double-sided VPC. So I won't go into the details of that, but it's one way that you'll make sure that you get the maximum out of 4 links that you connect between 4 devices. So this kind of a scenario is called a double-sided VPC. So there's one VPC on this entire system, not 2 or not 4. But if you go down from the 5000 to the 2000 to the UCS, you see that the same problem of redundancy exists. If your Nexus 2000 fails, there is no redundancy for the UCS. And if one of your Nexus 5000 fails, there is no redundancy for your FEX. Again, not a pretty way to do it. Okay, let's move on one more step further. We introduce not only a VPC between the 7000 and the 5000, but now we've introduced a VPC between the 5000 to the 2000. Okay, the advantage is obvious. Now, if you have a Nexus 5000 fail, your FEX doesn't fail. If one of your Nexus 7000 fails, your FEXs and all your links are still up and operating fine. However, if one of your Nexus 2000 fails, this kind of host connectivity still has a problem that, I only have single attached hosts. If something fails, I will lose them, right? So while legacy deployments do exist, I've actually worked with customers who have even the first option. Those are not the prettiest, and those are ideally not in today's day and age, right? With the kind of demand for redundancy and resiliency today, those are just reference topologies from the legacy world. This is how you'd want to connect, FEXs. So firstly, you have redundancy and active standby or port channel at the host level. Okay, some hosts support active standby with no port channel. What that means is if one interface fails, the other just takes over. But at any point, how many interfaces are active? Only one. Well, that's not this scenario. I'm not trying to lead you to that here, but in the scenario where you have active standby, at any point there's only one interface that's up. There's no port channel. So there you get the benefit of redundancy, but you don't get the benefit of load sharing, and you don't get the benefit of failure recovery in certain scenarios. So that's typically done by NIC teaming and active standby. Yeah. Good question, not yet. Yeah. So we'll come to that. I'm sorry? I cannot comment on the exact roadmap, but that's something that's being evaluated, right? So if there are enough people who need that feature and who come to us, we definitely would want to roll that out sometime, right? So here, this represents the best case scenario where you have a port channel going towards your host. So when you have actually two interfaces, you not only have active standby redundancy, you can actually use them active, and then pump traffic through all those links. Now, the inherent advantage is that, as you've noticed, while the Nexus 2K is just an external line card, you can still do a FEX going from, you can still do a VPC going from the FEX. So in this example, if you see this, these are two different FEXs, and they are connected towards one box, right? A point to note is that this topology between the Nexus 5000, the Nexus 2000, and the UCS, this is what is termed as enhanced VPC. A lot of you said enhanced VPC earlier. So the eVPC, the terminology eVPC is referred to as this Nexus 5K, 6K, and 2K combination where the FEXs are connected with a VPC to the parent, and there is a VPC going from the FEX towards the server as well. Enhanced VPC is only supported on 5K today. With the 7K, we support something called active-active VPC or active-active FEX. It's not the same thing as eVPC, but we'll see what kind of a scenario it caters for. This is the other, yes?
So do you require a port channel between FEXs in order to come to VPC, or does that go back to the parent?
Good question. So do you need a VPC from the Nexus to the parent? Well, there are no peer links here. Yeah, that's a good. Yeah, let me talk on that for just a minute. So that's a good observation here, right? So what he's saying is that your VPC here looks normal because hey, you have two switches, you have a VPC, and you have a peer link for it. Okay, sounds normal. All right, here you have two boxes here. You have a VPC going to each FEX, and you have a peer link here. That's fine. Look at this VPC, it's not. So here, well, this is not a VPC to start with. Yeah, so here, yeah, you got me on that. You got me on that. You did definitely get me on that, yes. For this VPC, here between the Nexus 2Ks, you use a peer link which is supposed to be here, which is not on the diagram. Everything's virtual, that's bad. Anyway, so the peer link that's actually used for building the VPC is that of the parent. You don't need one here. I definitely needed one here, but that happens. So let's just summarize, right? We've talked a lot about VPCs at different levels, right? The fundamental way you'd want to configure a server connectivity today is by definitely using VPCs at the server level. The only reason why you would not do it is if the host did not support a port channel. If you had a server with only an active standby NIC, then you'll have to look at other options. But if you had an option of a VPC, do a VPC. We offer a wide range of combinations to help you cater to each situation. So for example, in this topology here, the simplest one, you can see that you have two parents, straight through FEXs. So the way we connect this, we call this a straight through FEX. Reason is the FEX is only single home towards the parent, but you can still pull a VPC from each of these FEX. Each FEX does not need to be connected to both parents. You can still make a VPC out of this. So the terminology used here is these two are parent switches. These are straight through FEXs. And this is called a host VPC. Host VPC is typically a VPC you pull from 2 FEXs down towards a particular host.
But it's just a port channel to the hubs, right?
It's a port channel towards the hub. The difference is it's not only a port channel, it's also a VPC because it connects to 2 sets of switches, parent switches. So if these were, if there were 2 links here in a port channel and no link here, that would be a regular port channel to the FEX. This is not only a port channel to the FEX, it's also a VPC to the FEX. And the beauty of VPC is that your server doesn't really care or understand it. It just thinks there is one virtual device, but from the network point of view, it understands that there are 2 different devices. The next one is what we call the FEX active-active. So this design is supported on the Nexus 7000. We released 7.3 code where we started supporting this. I'm sorry, 7.2 where we started supporting this. The interesting thing in the design here is the question you want to ask yourself is what kind of a redundancy are you planning for, right? So this feature ask came from our customers, and the typical scenario they wanted to actually cater to is that they have servers. These servers either have only one link or they have an active standby, and you want to prevent a switch failure, right? Your parent switch failure from taking down an entire FEX. So in this topology, what will happen is if one of these switches fail, the parent switches, the FEXs will still be okay, because now you have a VPC that goes towards each FEX. In this, yeah.
But remember that FEX now has half the bandwidth that it did before.
Why would that be so?
Because if switch 1 goes down, FEX 100 is still up, and he's connected to switch 2, so the server...
In terms of bandwidth, definitely yes. So the bandwidth is definitely half the bandwidth, but in the alternate scenario, you had that FEX go down completely. So, well, see, if you lose a switch, you're bound to actually lose some interfaces, right? So when you lose those interfaces, the bandwidth will take a toll. So if you don't want that to happen, straight through FEX is the only option. So it's a decision you have to make, and that's really what I want you guys to think about, right? Because there's a whole bunch of combinations, and it's about what you want, right? You might have an active standby environment where this might actually work for you. If you have an active standby environment or a port channel environment, and with an active standby you only have either one is on or the other is on, right? So in such a scenario, if one leg goes down, the standby links take over, and then your oversubscription, your bandwidth is all the same. It doesn't change. So if that's what you want to have a straight through FEX connected like this. However, if you have other requirements where you want to protect from a single switch failure, then this is the design you want.
So which parent switch is in charge of which FEX for like upgrades or that sort of?
Very nice question. I expected this very, very nice question. Which parent switch is controlling the FEX, right? Both of them are. So ideally, you want to configure them on both the parents. So you have to configure them identically, but on both the 7K and the 5K, we support a feature called config sync. So you can really go configure it from one switch, and then it will get transferred over to the other switch. So you only have to do it on one switch, but it doesn't matter which one.
I assume there's some way when you run the upgrade process from the 7K that it won't
Yep.
upgrade both of them at the same time.
It won't. So there is a very nice way to, there's a good document out there which explains in a dual attached FEX scenario, what are the steps you need to follow so you can get a hitless upgrade. So it involves, I'll just come to your question in a second. It involves, it actually involves, upgrading from one side, and that connection will actually, it'll go out, meaning it'll say, there's an error in the version mismatch. So those links will be down for temporary sake, and at that time you'll be connected to the old one. And then you actually have the FEX upgrade, and then you roll it over to the newer one, and then you upgrade the other parent. So there is a good document that covers that process.
So, but am I to interpret that the 9A, in order to achieve the same topology, it has to be a double-sided VPC?
It doesn't have to be a double-sided VPC.
It's saying that this design is not supported on the 9K, which looks like a basic VPC.
So this design, meaning a VPC towards the FEX, is not supported on the 9K as of today. So with the 9K, you can use a straight through FEX and then use a VPC from the FEX going to your hosts. This is supported. As of date, as of now, right now, the 5K and the 7K support this. The 9K does not yet support having a VPC towards the FEX. Any type of VPC. So the VPC between the 9K and the FEX not supported.
So to fix this, you just connect your host to the parent switch with a VPC. Yes?
Yeah, so you do this. In this scenario, it is actually a VPC going to the parent, while the VPC is actually connected on the interfaces of the FEX. When you go to the parent and do a show VPC, you will see this is a VPC on the parent. So with 7.3 version, we enhanced our scalability as well. When we introduced this feature for 7K first, we had maximum of 15 active VPCs in the FEX. With 7.2, with 7.3, it's about 32, and we can have 32 active FEXs. So there are a few other limitations. We don't support layer 3 ports on the HIF when you do VPC, active VPC, and we also don't support VPC plus over an active VPC. So VPC plus is basically running VPC plus fabric path in the same domain. So when you do a fabric path and a VPC on the same switch in the same domain, we term that as a VPC plus. So active does not support VPC plus. And then there's the final one, which is the eVPC or the enhanced VPC, which is supported only on the Nexus 5Ks. So this is a very specific niche use case scenario where you have VPCs going to the FEXs as well as VPCs going towards your servers. In most scenarios, if you're using the 7K, in most scenarios, the FEX active takes care of your redundancy at different levels, right? Again, you need to understand what kind of redundancy requirement you have. You don't need to have VPCs at every level just to be redundant, right? If you have a particular type of network, you can, you anticipate a particular set of failures saying, I want to be covered against this, failure of a FEX or a parent, and correspondingly, your servers will have different kind of connectivity, which should take care of your redundancy. Last concept here, before we move to the last section here, is about physical port VPC. Now, this is a concept where, normally the VPC configuration is done on a port channel, right? So instead of having the port channel in addition to a physical port, when you do that, you say interface 101/1/1. You put it in a port channel, like, for example, port channel 1, and then you attach a VPC to it. What happens when you do that is you burn more number of virtual interfaces, because there's a virtual interface for your port, and then there's a virtual interface for your port channel as well. But in a lot of scenarios, your servers only connect through 2 links. So on each FEX, there is only 1 link. So you're creating a single link, and you're also putting it in a port channel to be able to do VPC, right? So while that affects our scalability, what we did is we introduced something called physical port VPC. If you see the configuration here, there is no channel group 1 mode active. There is no port channel configured here, there's only a VPC here, and that VPC is directly on the physical port. It's not on the port channel. What we do is we actually end up supporting a lot more of number of VPCs on the FEX if there are only 2 ports across 2 FEXs. You can't do this. I know this is a ridiculous slide, but a VPC is a 2-switch concept. You cannot infinitely pin them and have the world's most resilient network. No, you can't do this. Just a note. Yeah, there's a question, I believe.
I was going to ask, is there anything other than the number of VPCs that can be created using physical VPC versus creating a port channel and putting the VPC on the port?
It's just the number. It's the scalability. So we burn more number of LIF interfaces, and on the parent there are only so many available. So for us to scale more, and this environment in servers that only have 2 interfaces, you never have a VPC with 2 ports on the same FEX, right? You don't have a 4 port. So that's the scenario we built this for. I do encourage you guys to take a look at this reference document here. It's one of the best references I would recommend. So it talks about each of these scenarios we discussed, and it gives you a table that says which platform supports what. So do take a look. So a quick run through of VXLAN support. Now the 5600 supports VXLAN, as you might know already. So we support VXLAN VTEP termination on the 5K itself. So all of this is supported. We support VXLAN VTEP termination on the 5600 using a FEX to connect to the end host. So if you see here, all the VTEPs terminate on the 5600, and then the actual endpoints are actually, the hypervisors get connected towards the FEX, and the VTEP exists only on the 5600. This is also supported. The next thing that is supported is a VTEP on the 5600 and a direct connection to a hypervisor on the parent port and the VTEP on the hypervisor, right? So if your VTEP is actually extended towards the hypervisor connected directly, this is supported. You may have different types of connectivity here where you can do this. The point is that this slide here tells you about the fact that we cannot have VTEPs on the 5600. In addition to that, we also have VTEPs behind the VTEPs. You cannot tunnel twice with VTEPs on the hypervisor as well. So this topology is not supported. So you can only do VTEPs on the 5600s or the VTEPs on the hypervisors themselves. You cannot do both. So none of these combinations are supported. Maybe dual home FEXs, single home FEXs. The fundamental concept remains that you cannot have VTEP termination on your 5600 as well as on your hypervisor. Okay, as we are nearing to the end of this session slides, I can assure you that there aren't too many left. Here's a quick view of how configuration goes, and for those of you who have not gone through these, it's fairly straightforward to configure a FEX and install it. You have to do the manual connectivity, but other than that, you just go around, saying feature FEX, which enables the feature. You configure the FEX port channel, interface port channel 100. Then you associate it in a very special way and call it switch port mode FEX fabric. So now the parent understands. And remember, to your question, all of these configs are not on the FEX. These are all the configs that go on the parent side port. Okay? So you just make the parent know that you expect to see a FEX coming on this interface. So what that configuration really does is it enables the protocol called SDP, which is a satellite discovery protocol. So it listens actively to SDP messages coming from the FEX. You associate it to a FEX number 100. So this will get pushed to the FEX. The FEX knows what it's numbered at. And you also make that interface a part of a VPC. You do that and give it a few minutes. The FEX will boot up. It will download microcode from the parent. It will sync up, and it will come online. Okay. And once it's online, this is a show FEX, a brief output of show FEX. You can see that the version it's pulled is actually from the parent. So the FEX does not have its own NXOS code running on it. It actually fetches it from the parent, microcode from the parent. Model number, serial number. What is the fabric port control link, which is the link that you connected to the fabric? And what are the other fabric interface states? So you can see that it's a 2 links connected, Ethernet 2.5 and 2.6. They're configured as a port channel 100. And the control link out of the lot, the control one is 2/5. Okay. Now, okay, that's how you configure a FEX after you had the FEX, right? But there is real usefulness in pre-provisioning of FEX. Especially when you do upgrades, it becomes essential for you to let the system know what FEX to expect before the FEX is actually connected. So even without the FEX connected, you can pre-provision it. You can just say slot 101, provision model number, and then when you do show run interface, you can see that when you do a show FEX also, you can see that that FEX is actually provisioned. The interfaces are not there, nothing will be online, but the system knows that it's supposed to expect a FEX of this model on that link. A pointer for all of you to note, it's extremely useful in a hitless upgrade. So when you're trying to do a hitless upgrade, one of the steps involves you configuring and pre-provisioning your FEX when you sort of roll over from a new version, old to new version. Yes? No. Until you actually have it connected, nothing's going to change. No, that's not possible. Yeah, I definitely do understand. The reason why this feature actually came out is to support. The fundamental point is that in one of the processes we do when we talk to a FEX, there is a reboot that happens. So the FEX is actually given a microcode, and it has to actually sort of go through a transition and get rediscovered. By doing the FEX pre-provisioning, what we do is we avoid one of those steps. So in one of the upgrade methods, you would actually benefit from not having that FEX reload.
And people should not forget, you can't configure a line card until you've inserted the line card.
Absolutely.
These are line cards.
Yep.
And it's nice that you're helping out with the particular code download. But at the end of the
Absolutely.
day, it's a line card until the line card's there. And if the line card goes away, your config can go away.
Yep.
Unfortunately, it serializes the workflow.
Yeah. You know, we can actually talk further on your question about configuring the interfaces. Just a little short of time, but feel free to talk to me right after. I have some details which I can talk to you about further, right? So when you want to troubleshoot, and the question that somebody asked about the counters, here's where you can see the counters, and here's how you can see them. Show queuing interface, and then this is the HIF interface number, right? So once you give this, you can see what are the QoS configs, the queuing configs, and what are the drops that are seen on this. So these are the drop counters. This is ideally where you want to watch out for drops. So that was the 2248 TPE, the earlier one, and this one is the 2348 UPQ. Okay, so last few set of things, Ethernet flow control. Why is flow control important? Because especially with some older generation FEXs, flow control is extremely important. Primary reason being FEX is the one that's closest to the source, right? So if your host is sending traffic in that direction, the H2N direction, so if there is a lot more traffic than can be handled on the network, the FEX is the last hop before the host that it can actually push the host and try to make it stop sending that much, that many bursts. So flow control is definitely required. In the in, we have it turned on by default. In the out, we don't. But it's always a good practice to have flow control turned on, because if there is an anticipation of a drop, flow control will kick in right before it happens, not after. The key point to note is that internally, especially on the 2232 generation of FEXs, we kick that in. There's a threshold internally on the WRED and the queuing mechanism, which when we near the threshold, we start doing the flow control, not right after. So if there's a possibility for the server to slow down, that's the best way to use that feature. I will not go through the entire slide here, but here's another example of how you can configure FCOE. So it's pretty straightforward. There are some things that you have to do. It's not a two-line config, but it's pretty straightforward if you understand FCOE configuration. Here's a detailed verification. So you can see that when you do a show FEX detail, you can, in one of the section here, you can actually see historic logs. So these set of logs are stored in NVRAM kind of memory, non-volatile memory. So you can go back in time and figure out where it, where the issue was. I'm almost at the end of my time here, and here is a quick view of how you can configure FEX with ACI. I leave it to you for reference. Last section we'll run through very quickly is connectivity options, right? So you have a whole bunch of 10 gig and 40 gig connectivity options. 10 gig, most of you would be already aware of SFP and SFP plus connections. So you can use a whole bunch of whatever is supported for each platform. You can use the SFP plus downstream. For the upstream, you have either native QSFP or QSFP to 10 gig breakout. So you can use the, in this example, you can use the QSFP as a single 40 gig QSFP, or you can break it down into 4 10 gig links. So a huge bunch of different cables are actually supported. Some of them, as a gentleman said, are direct attached cables. So you have the transceiver and the fiber fused and attached already. and many others are the typical transceiver separate and cable separate options. So typically the fused ones are for shorter distances, which if that's your requirement, then they are, for lower power requirements, they fit the bill. Can we, can we just take it offline? We'll try it at the end. So when you use the QSFP, you might have encountered the OM3 MM cable, the multi-mode OM3 cable. So this is a type of a parallel looking MTP connector, just to show you how it looks internally. Externally, this is how it looks. What it actually has is it has pairs of connectivity, right? It has many pairs. It has 12 pairs of connections across the links. What happens is, for the 40 gig connections, we actually use 8 sets of pairs, and 4 pairs, fiber pairs, are actually unused. But that's how the MTP connector is, and typically you can use that for a 40 to 40. Now, in case you use a 40 to 10, what happens here is that the same kind of MPO connector is on one end, and then you split that into 4 into 10 gigs. So because we have 12 lanes inside, we can bundle them up separately. So a 40 gig interface can operate as a 40 gig, or it can break down into 4 into 10 gig as your need is, right? So we have cables that directly give you a QSFP to 4 10 gigs. So you'll have a QSFP male SFP on one end, a QSFP on one end, and 4 SFPs on the other. You could alternately also use the MPO cable and then attach your own cables and pull out 10 gig options out of that. A gentleman asked about BiDi transceivers. We definitely do support BiDi transceivers. It's one of the great innovations that we've done in reducing your cabling costs as you move from 10 gig to 40 gig environments, where we reuse the available cabling and we let you have 40 gig connectivity speeds without spending a bomb on new cabling. And this is something that you'll see a lot in such deployments, that your FEX costs are a particular number, and typically fiber connections or cabling costs are more than what it costs you to get a FEX. So typically BiDi offers you a huge advantage in terms of cost savings if you choose to go the BiDi route, right? These are example of some of the cables. As I said, this is the first one is MPO to MPO cable, which is a 40 gig to 40 gig direct, and then you have the CSR4 to the breakout, which is 40 gig then converting to your LC type 10 gig connector. So you have 8 of them, so 4 pairs of 10 gig connections. We have the SRBD as well. This supports extended length. Again, multi-mode LC duplex is not supported. We only support it with the BD. So with breakout, we don't support it. With direct 40 gig to 40 gig, it's supported. So you can only do this with QSFP. You can only do it with 40 to 40. You cannot break this connectivity down. Again, as I said, you have a huge number of choices. Again, please go back and verify a compatibility matrix of which FEX supports which kind of optics, and make sure that you do that homework before you actually go and buy in to a particular set of cabling choices, right? FET is the last thing we'll talk about today. I'm just over time right now, but FET is an innovation that we made where we offer transceivers that are typically made in mind of the FEX connections to the uplink. Right? They're low-cost QSFPs that are tailor-made for this kind of solution, and they will only work with this set of devices in these forms. So when you use, for you guys who are planning on ordering FEXs, please know that you have bundles available where the FET is included. So the uplink connectivity option in a FET is already there. It's a cost-efficient way of using FETs.
When you include the FETs with the product, does that also include the MPO cables?
No, the MPOs are completely different. So a bundle will only include FETs. So if you choose that bundle. Okay. So QSA is an adapter that converts 40 gig to 10 gig. It's not 4 10 gig, just one 10 gig out of a 40 gig port. All right, so those are the options we have in terms of connectivity. We've talked about design, we've talked about architecture, we've talked about connectivity options. So that brings me to the end of my session. A few key takeaways for me that you would take from the session are to realize what the benefits of FEX are, what are the supported designs, and then take that and evaluate it against your requirements and try and find a fit, and then use the benefits of FEX. All right. I've put quite a lot of slides on the appendix as well for you guys to take a look at later on. You may download the slides. Please do complete your evaluation, and that's about it. Thank you guys for your time.